All right. What I want to do today is finish an entire curve sketch based on what we covered on Friday. Friday we were looking primarily at just getting this sign diagram right here. Okay, and we said that you need to incorporate a couple of things into your sign diagrams. One, where we started at first, we were using the critical values. We found a critical value at 0.8 and at 5.2. But we said on Friday, you also need to incorporate anything that is eliminated from your domain. In this case, we had an x squared minus 9 in the denominator, so x plus 3 and x minus 3 would be in our domain, or would be eliminated from our domain. So those we include here as well. Because anytime we have points like this, we're either going to have an asymptote or a hole. Okay, and we're going to look today at how to determine or how to use those in sketching our graph. Okay, but if you recall where we left off, we had found the derivative of this function. We had set it equal to 0. We had found the solutions, and we said, okay, -3 was a root of that numerator, but the denominator was x squared minus 9. So obviously, -3 wasn't allowed to be a solution to the actual equation. It wasn't an actual critical value because it's not in the domain. Right? But that did allow us to find this x squared minus 6x plus 4, which gave us the two critical values at 5.2 and 0.8. Okay? So, once we found those, we put those on our sign diagram along with the -3 and +3, and then we plugged in values in each of those intervals. Those 4 points divided our entire graph into 4 intervals. And we evaluated that in f prime. Okay, we picked a single point in each interval. I did -4, 0, 1, 4, and 6. The nice thing we said was, if you look at your derivative factored out, okay, this is x plus 3 squared, so no matter what we get, it's going to be positive. This is x squared minus 9 squared, so no matter what we plug in there, it's going to be positive. So really, the determining thing that will tell us whether this is increasing or decreasing, whether our derivative is positive or negative, is this part right here, the x squared minus 6x plus 4. So that'll save you some time evaluating. When you plug in -4, you can plug it in just to this x squared minus 6x plus 4. Alright, so I did that with all these. I got positive, positive, negative, negative, positive, which means our graph is going to be increasing in this interval, increasing on this interval, decreasing on this interval, decreasing on this interval, and then back to increasing on this interval.
On the quiz, will there be like a whole bunch of possible roots, like for division?
No, I kept it so you're not. I'm testing you over whether you can do this, not over the rational root theorem. So. The last thing, now we can factor the original function and find zeros to determine whether x equals 3 and x equals -3 give us a point discontinuity or an asymptote. Also, like I said, we're finding zeros, which are points on the graph. So now what we're kind of doing is we're moving from the derivative to, we're actually taking a step back to what you did in SL1 in graphing functions. So now we're going to do all that stuff and kind of put it together. And then once we're done, we'll actually talk about what I would recommend using as your kind of sequence as you're doing these. That would probably make it the easiest. Alright, so here's what we're going to look at. We have our function, we have our domain, we need to find the zeros of this function first of all. And to do this, this will also help us identify whether 3 and negative 3 are asymptotes or wholes. Well, what I'm going to do is I'm going to factor my numerator and denominator. Okay? So my numerator, I'm going to group these first two terms and factor out an x squared times x plus 3. I'm going to group my second two terms, and I'm going to factor out a negative 4 times x plus 3. That whole thing is over x squared minus 9. Okay, so now my numerator factors into, I have a binomial common factor of x plus 3, so I pull it out, and I've got x squared minus 4. My denominator, x squared minus 9, factors into x plus 3 and times an x minus 3. Okay? At this point, we can figure out what 3 and negative 3 give us in our graph, and we can also state what our zeros are. Okay? Notice here, this cancels out. So what do I know about x equals negative 3? It gives us a whole. Alright? And I'll call that point H. It's going to be negative 3, and then how do you find the y coordinate of the whole? Plug it into...
The original? No.
If I plug it into the original, I'll get something undefined.
Alright.
Do you remember? We'll plug it into what's left over after we cancel out what gave us the whole. So I'm going to plug it into the x squared minus 4 and the x minus 3. Alright, so 9 minus 4 is 5. Negative 3 minus 3 is negative 6. So it's a negative 5/6. Yeah. Here?
How do you go from x squared times x plus 3 minus 4 times x plus 3 to just 1x plus 3? How'd you like?
It's like, this is our factoring by grouping. It's like we had this. And I factored out that common factor. Okay?
Yeah.
It's just our common factor, instead of just being
So
a single thing like a y, it was an x plus 3. So. Alright, so there's a whole. X plus 3 gives us, or I'm sorry, x minus 3 tells us that x equals 3 is what? No, it's an asymptote. Remember, if you have things eliminated from your domain, the negative 3 and positive 3, if it cancels out, it's a whole. If it doesn't, it's an asymptote. Okay? And then finally, our numerator, x squared minus 4, that tells us plus or minus 2 are the, what do we call those?
I want to say horizontal asymptote, but it's not that.
No. Yeah, the degree's bigger on the top, so we don't have to worry about horizontal asymptotes here. They're x-intercepts, or zeros. Okay? These are our x-intercepts, or zeros. So, let's kind of take into account everything that we have. Our whole, I'll write it down here, is the point negative 3, negative 5/6. our asymptote is x equals 3. Our zeros are plus or minus 2. And then we also have a y-intercept. The y-intercept is so easy to find. I always find it just to give us one more point to help us with the shape of our graph. Okay? So the y-intercept, all these x's equal 0, so I just have negative 12 over negative 9. So that's our point 0, 4/3. Okay? So now we have everything we need. Now we can actually sketch this thing. Okay? So let's work our way through it. Let's start with the zeros. My zeros are at 2 and negative 2. I'm going to put a little z next to both of those so I know what they are. Okay? My y-intercept is the point 0, 4/3. So we'll put that right there. Then I have a hole at negative 3, negative 5, 6. So here's negative 3, negative 5, 6. Then make sure you actually make it a hole. And then of course you can see I already have my asymptote at x equals 3 drawn. Okay? Now, 2 more actual points that I need, and then I'm going to use my sign diagram to help me sketch everything else. Okay? Our max point. Our max is going to occur at 0.8 something. Alright? So this is where your calculator comes in handy. If I plug in 0.8 into the original function, what do I get? Someone else could work on 5.2 to get our min point. Okay?
How did we get from
Those were our critical values. Remember we set our derivative equal to 0.
Oh, this is from like last week?
Yeah, this is from Friday. Friday our focus was on just getting that sign diagram. So today I want to kind of take us to the next level here. What did we get for the max point? 1.53. Okay. So our max is at 0.8, 1.53. That's our max. It's just barely above the y-intercept. It might be good if I made that point a little smaller on my y-intercept. Okay. Because that was just at 1 1/3. Okay. So there's our y-intercept, our max point, and then what do we get for the min point? At 5.2. It was 10 point something. You guys are the ones with the calculator, so. $10.47. Okay. All right.
Yeah.
Some breaking news. Okay. Sorry, it's probably just someone else getting arrested. We're traded, one of the two. So. All right, so we have 5.2 and 10.47. Okay. And that's a min point. Alright, now that looks kind of strange until we look at our sign diagram. Okay, so we have a min point way up here and a max point way down here. But let's look at our sign diagram. Okay, first of all, to the left of our hole, it's increasing. So I know we're going up towards the hole. Alright, and I'm actually going to draw it like this. Because there is one feature that we haven't dealt with, and that's okay, because that's beyond what we're studying. And that is, there is what's known as a diagonal asymptote. That this actually does have, but like I said, that's beyond what we're looking at in this study. Okay, so that's why it doesn't go down more; it goes kind of diagonally more. Okay, then from our hole to the max point, we're increasing. Okay. Now, as I increase towards the max, notice I should hit my 0 and my y-intercept as well. Okay? If at some point it doesn't make sense to hit those, then you know you did something wrong. Okay? Now that I hit my max point, the reason we knew it was a max point is because it changed from increasing to decreasing. So now it's going down, and it's going to go through my 0, and it's going to approach that asymptote. Now, you'll notice to the left of the asymptote we're decreasing, which we already can see there, but also to the right of the asymptote we're decreasing. Okay? What typically happens as we go down here on the left of the asymptote, what typically happens on the other side? We've seen this before.
Reflection of it.
It's got to be decreasing. That's what the challenge is. But usually, what do you mean?
That needs to be asymptote.
Okay, but we're doing that on the left side. So on the right side, it'll
This.
yeah, it'll come down from the top. All right. So as this was the thing with asymptotes, where on the left-hand side we approach negative infinity. On the right-hand side, we're approaching, or it's coming from, positive infinity. It makes this jump here. And then it's going to hit our min value and end up going like this. Because after the min, notice it changed from decreasing back to increasing to the right. Okay? And by the way, here's that diagonal asymptote I was telling you about. It's going to approach that line up there. It's going to approach that line down there. You don't have to graph that, but FYI. Yes?
Why don't we have to consider the y-asymptote? Or if there is
A horizontal asymptote?
horizontal asymptote?
If there were one, you would need to consider that. In this case, though, notice the degrees. The degree of our numerator is higher than the degree of the denominator, so we don't have a horizontal asymptote. Yes?
When you start the graph, how do you know where to go up from?
Here's the deal. Because we're not studying diagonal. You're right. Because we're not studying diagonal asymptotes in this course, if you had done this, I would be fine with that. Okay. Yeah, I just did it because I knew that existed, so might as well do more accurately. Alright, so does that all make sense? It's kind of disjointed the way we handled it because there's so much going on. Alright, and that's why I want to kind of summarize this whole process, and then I'm going to give you guys time to try working on some stuff here related to this. This is just my recommendation. Obviously, we did it in a different order. We did all our critical values and stuff first, and then we went back and found our zeros. Part of the reason it was difficult to find our critical values is because we didn't recognize that right here we could have actually reduced. Okay, and if we had found our zeros first and seen what this came out to in a factored form, it actually could have helped us reduce that, and it would have made solving it easier. Okay? But that's part of this process. I want us to kind of see, you know, why what I'm recommending here might be best. Okay? So here's what I would recommend doing. Start with the really easy stuff. Identify your y-intercept, identify your domain. Get that out of the way right at the beginning. Then secondly, find the zeros of the function. So basically, these first two steps are SL1, chapter 2. Okay? Then is what we've been looking at. Find your derivative, set it equal to 0, and find those critical values. Once you do that, you have the domain, you have the critical values, then you can do your sign diagram and determine those intervals where it's increasing or decreasing. Then, once you see where it's increasing and decreasing, you can determine the max or min points. And then finally, it's basically connect the dots. Okay, because you have a whole bunch of points already there. You have asymptotes or holes or whatever you need. And now it's just to use your sign diagram and the points that you have to finish off your graph. All right, any questions? Okay. Now, what I'm going to have you guys work on here, the problems from the book, they don't have you do the entire sketch all the way through. They kind of have you do bits and pieces of different ones, okay? But that's okay. I mean, if you can do all the bits and pieces, then just sketching a whole one is just putting it all together. But I want you to take some time here, the last 15 minutes or so, and try these. You can jump around in the and trying different problems, okay? Remember, when they say stationary points, those are the same thing as critical values, okay? Just a different term for it. So, that'll be it. I'm going to let you guys get working on that then now.